session. We have Sanjeev Arora from Princeton, who I think needs no introduction, but has both done a lot of foundational work in theory of computer science and learning theory, and more recently has been explaining deep learning and is going to be talking to us about emergence in language models.
Thank you. Yeah, great workshop. This is joint work with fantastic collaborator Arora. If you haven't heard of so far, you'll be hearing much more. And I just also wanted to advertise this new unit that was started at Princeton, which is Princeton Language and Intelligence, which is devoted to large AI models. Okay, so emergence is this phenomenon that when you scale up LLMs from, say, n parameters to 10n parameters in tandem with dataset scaling, as you saw in the previous talk, it is accompanied with significant performance gains on many benchmark tasks, few shot or zero shot. And the related view is that emergence is actually ability for in-context learning. That the model doesn't even need any explicit training to do to solve tasks. You just present the task to it in natural language and it does it. So that's an alternative definition that some people have. But obviously, if you're looking at the continuous phenomenon, that's the first one, that there are performance gains. And scaling laws are primarily about cross-entropy laws. And this is the chinchilla law that, with the number spelled out, that was alluded to in the previous talk. So here's the thing that I was going around also at DeepMind and asking people, what do you find weird about emergence? And one very good researcher who had a statistical physics background and so on, so really understands technical things, said, I don't understand why reducing the low order term. So like this, as was pointed out, 1.61 is something fixed related to the language. And then the terms that are going down are these other ones. And when you increase n by a factor of 10, n and d by a factor of 10, you change these terms, the additional terms, by some small amount, like 0.06 goes to 0.03. Why the heck should that change to, why does that lead to such big differences in macro behavior? So we'll get to that. So, but here are the plots, which you also saw in the morning session. So, for different tasks, you see that for a while, as you scale up, nothing much is going on, and then suddenly performance starts improving. Okay, and actually in this wear out paper, they also note that there's an elbow in the performance for cross-entropy loss at around that time. Okay, so we'll try to address that with theory, but I want to also point out this one phenomenon, or this one skill, meta skill, which is ability to combine skills, okay, on demand. So this is related to in-context learning, but also the essential function of a chatbot, an interactive agent. So for instance, this was an actual query I would give to the language model and say, like this, I want a single example of 2-3 lines of text that illustrates these different things, which are captured by NLP tasks often, and anaphora resolution, logical inference, simple physics, and judging sentiment. Can you give me one, please? So GPT-4 says, the cat chased the mouse. It was very small. The mouse ran into a hole in the wall, and the cat tried to follow, but got stuck. Looked very funny, and I couldn't stop laughing. So it's addressing all the constraints that I set out on demand. Okay. And now, we've seen this before in the talks and the Sparks paper and whatever. People say, it was in the training set. So you can you can put more constraints. So you can say, how about giving an example in context of hip hop, or something even more esoteric, medieval chivalry or something, right? Plenty of physics needed for chivalry. All right, so Big Bart, so I'm switching to other models. Big Bart says the rapper dropped the mic and walked off the stage. He left, so he's, of course, an Afro resolution, left the crowd roaring in approval. Claude Instant, another good model out there, has something about Lil Wayne. And the base is reverberating, so that's simple physics knowledge, right, about the world. And the size exceeded Dropbox limits. Okay, so you can continue on with this, okay? So you can put more constraints and see what it does. And the point is, okay, actually, I'll get to that in a second. I'll get to that example again. First, let me just say now, so with everything I've said so far, I want to first now say what are the stumbling blocks for theory before we go on. So very little mechanistic understanding of deep nets. Deep learning is still not understood very well theoretically. No clean definition of the problem. What is skill? What is combination? What are tasks? And there's plenty of work in linguistic theory for the last many decades. And you end up with some formalizations like context-free grammars, probabilistic context-free grammars, Christian logic-based theories, etc., and probably many more that I don't know. And they end up being formal and rigid. Like you can't say, given natural text, you know exactly what's going on. And is it being generated according to some of these things? Then suppose you even solve that problem, right? You had a formalization of what is language and what are skills. How do you argue that a large subset of them emerge roughly in tandem as the cross-entropy loss increases? Okay, and of course, we don't have any mechanistic understanding of deep nets. Fourth, why do combinations of skills also emerge? That, as it gets better, actually it's able to combine skills flexibly. And so this was my point that I was about to make on the previous slide. That suppose the number of skills is, in the thousands even. That's a very comfortable estimate. If you linguistic skills, logical, world knowledge, all those kinds of things.
Wait, can you define a skill?
I won't, and I won't need to. Yeah. So I'll just use your intuitive definition. And so grant me that there are 1,000 skills at least. 1,000 to the power 5 is 10 to the power 15. And remember, I'm also going to ask it to generate, in some very restricted domain, medieval chivalry, which is only a tiny fraction of the training set. So for sure, with high probability, if I take a menu of 1,000 skills and randomly pick 5 and a topic, an esoteric topic, this is almost certainly not in the training set. Nothing remotely like that. Right? So this was a simple way, like all these doubters, it's in the training set. It's not in the training set.
Well, wait. You're assuming that, this is all, sampled randomly, whereas you're a human writing these things, and the people
No.
training set are also humans.
No.
You're on the manifold of what humans are interested in.
Take 1,000 skills. You give me the 1,000 skills. It could involve coding, whatever, anything, right? Math. And I'll take a random subset of 5 of them and ask the model. There are 10 to the 15 combinations. Like, in order for this to not be, vastly more than the number of training set, you would have that every paragraph is about, 10 to the 1,000, 10 to the 5 combinations. That doesn't make any sense.
No, but I don't know. You're defining skills. Some of the skills are very easy to data augment, for example. Others are not.
So I'm not saying this means that the AGI is here, right? That's not what I'm saying. Right. Yeah. I'm just getting around that usual objection somebody pipes up. It's in the training set.
No. Look, I think this is, you cannot.
Okay, I don't want to talk too much more about this. Yeah. Right. This is not important. Yeah. Okay.
So when you're saying we can't have 10 to 15 examples and so on, an example doesn't have to include only this subset and exclude the rest and so on, right?
That's
You're
fine.
demanding too much of the example, maybe.
But any way you do the math, you won't have 10 to the 15. Yeah. I mean, even if there's collisions. Yeah.
I think the point being made was no one's actually tried to
sample 5 random skills and test?
I did.
You did.
But you don't have a definition of what the skill is.
Doesn't
How do you
matter.
randomly sample?
How does it matter?
Well, the randomly
Do we
sample,
agree
you
that-
don't know what you're sampling from.
Doesn't matter. Like if you have 1,000 skills and you and I agree that these are a subset of natural skills. If I take a subset of 5, it's
But I don't know what a skill is even.
It doesn't matter. For the argument, it doesn't matter. If we agree that it's a skill. Yeah.
Maybe, Sanjeev, I think the question may be more like, did you actually enumerate 1,000 skills and were you able to
Yes.
to your satisfaction?
Yes.
Okay. That's
Is an argument is if, for example, in the images you had like 2 to the n pixels, you have the n pixels and 2 to the n possibilities and you don't enumerate all of those. So do you see this being different than
I think it's different.
the exponential complexity of
So the question was, is this the same as, n images with n pixels that have 2 to the n possibilities? That's not what, yeah, I think so. Yeah, okay, let's not ponder too much on this. My point was, I think everybody agrees that you can give GPT-4 crazy things, instructions, and it does something reasonable, right? That we agree on. Let's start with that. So this also relates to, this debate about, stochastic parrots and AGI and so on. Now, I don't want to talk about AGI. I mean, that's a very loaded term, but, at least the stochastic parrots critique, right? So, and there was this very nice discussion that Andrew taped with Jeff Hinton, where Jeff was saying, look, the one basic thing we have to do is, in this debate, is to agree on the facts. And the key fact from his perspective was, and this was quote, are these chatbots mere stochastic parrots, or are they beginning to understand us, right? Understand us and our work. And it's not clear what that means, right? But certainly this kind of thing suggests that it's able to put itself and imagine itself in these scenarios, which are not in the training set. Very minimal form of not being a stochastic parrot. That's all I'm saying. So yeah, so with Anirudh and Jonah Brown-Cohen, whom Berkeley people might know, is now at DeepMind. We did some experiments by ourselves, so we were the raters, and at least GPT-4 did reasonably well. And the other models start to struggle. 3 skills, fine. 5, 6, they struggle. But these were very, I wouldn't say they were very exhaustive experiments. Are we on the same page? Let's go on. All right. So clarifying the emergence question, but also a theory overview. So here's a motivating example. Exactly, right? What are skills? So the old example that everybody in AI knows, Winograd schema from 1971. The city councilman refused the demonstrators a permit because they feared violence. Everybody knows what this sentence means. But if you start thinking about it, they is actually ambiguous. It could refer to either the city councilman or the demonstrators. But somehow we knew immediately that it referred to the councilman. So, well, does a model understand it? So you can add what's called a closed prompt. Okay, just multiple choice. Who feared violence, councilmen or demonstrators? And until 5 years ago, models would be 50-50 between the two. They had no clue. So they hadn't figured out anaphora resolution. That's called anaphora, they. What is it referring to? Question for you. What skill or skills are used in this example?
You're the one talking about skills.
No. I'm just trying to motivate discussion. Like, what are skills?
I think it's just, a whole bunch of co-occurrences.
Skills is a whole bunch of co-occurrences.
No, the reason that this works is there is a lot of co-occurrences that all point to the right answer. There might not be any explicit skill. Skill can be a mental construct that doesn't actually exist in the data.
Yeah, so skill, so for example, we agree that parsing or understanding, what is refused, what is a permit, right? What does it mean to give a permit to demonstrators? What does that even mean?
I don't think you need any of that. No, it's correlations. You might not even need words. You might need,
What is not a correlation? Everything is a correlation.
Yeah.
So then we have to use some like skill definition. So that's his point.
Well, but where is this
You think
definition?
you are doing this by correlation, not by.
Yeah.
Okay. Well. Okay. So you yourself think that you're not AGI. Okay. Good. All right. Okay. So. All right. But okay, everybody else I hope gets the point, right? That there's logic being used. There's world knowledge. There's causality,
No,
right? There's
wait,
because.
logic. Like humans are really bad at logic.
Not complete and sound. You know, because. What is because, right? It's causality. You don't agree. All right. Okay. So if by your definition, then you are not using any skills.
No.
Okay, good. All right. So that's useful. Yeah. So I didn't know that point of view. Yes, that you're that. Okay. All right. So okay. So
So can you go back?
yes.
So what skill are they using?
Good. All right, I forgot to say the punchline. Thank you so much, Shafi. What skill was used to answer this question? And the answer is all of them, right? You have to understand what's because and causality. You have to understand what are demonstrators and why they need a permit. You have to understand when violence happens at a demonstration, is it caused by the people who gave the permit or who got the permit? All of that, right? World knowledge, everything. Yes, yes. D.
In this case, if we think in this way, we have a lot of sentences like this. If we ask a human to annotate, just like what you did, like an expert going through that, listing all possible skills contained in all sentences, does that mean that in the pre-training model already see all those type of skills?
So I'll get to that, yeah. But I think the number of skills, I think, is small. Maybe it's in the tens of thousands. I don't know. We can discuss hundreds of thousands. But I think all skills are there. But maybe not with enough.
Questions.
Good.
Sorry.
Yes.
I remember, it's been maybe 30 some years, but I think, fifth grade or something, we just go through and say there's a noun, there's a adverb.
Yeah. That's parsing.
If we parse this, wouldn't there be a token that basically gave the right answer?
Because they could refer to either city councilmen or demonstrators. It doesn't make sense for them.
In the corpus of human language, wouldn't it always refer to the first thing that you use? Or maybe not?
Yeah.
No. It doesn't, okay.
So there's
Because they were
skill here. So there's only one agent.
Fair enough.
What agent?
The councilmen are the agents.
Yeah, no, there are all kinds of, how it's solved is not going to be a concern here. Yeah.
Change it to they like violence.
Excuse me?
What is the connection of all these skills with the final block?
Yeah. So let's go to that. Yeah. Maybe unless if there's a really burning question. Yes.
Just a quick question. Could you have asked GPT-4 to tell what skills it used to come up with?
It doesn't have that level of self-introspection. No. Yeah.
If you say that it used all the skills to solve this example, then what's the point of mixing 5 skills?
There's no point of this example except to illustrate that skills are mixed up and it's not easy to separate out what skill was used. That's the only point of this example. Yeah. Okay. So, all right. So now let's see what does that have to do with reduction in cross-entropy, right? So just to get an insight, what's the connection? So remember this question from my colleague, like why does this low order term, given how large N and D are, why does that small change matter? The insight is this. There's a base entropy. This point was made earlier in the earlier talks. And then there's the excess, right? And this excess is the one that's going down from scaling. When you scale N and D by about 10, that excess goes down. Okay, that's a factor 2. That's exactly what my colleague was saying. But a 2x reduction actually is very significant. Let's see with that example. So here's the example. A model that was 50-50, right? The model's 5 years ago. A model that was 50-50 between the two examples had log 2 excess cross entropy, right? So if you just present that, to the model, to a good model, it would say, answer was A, and so it gets excess cross entropy log of 1. It's deterministic, which is 0, and the model that's confused gets excess cross entropy log of 2. large constant.
So this is you're working backwards from the fact that it was 50-50.
Yes. So the perfect model or human gets log 1. Let's call it human. Gets log 1, which is 0. And the bad model gets log 2. Okay? So that is the definition of excess, right? So this corresponds to the base entropy, right? There's no entropy there because the human is perfectly confident. And the model is getting log 2. So all of that is the excess term. Yes?
We know for a fact that humans get this correct.
Let's assume it's 1. For sake of argument, yeah, let's say it is actually perfect. Yeah.
I'm sorry, Sanjeev. There was a calculation you were doing here.
Yeah.
Which I'm not sure I followed.
Okay.
But, I mean, I saw the working backwards to get log 1 and log 2.
Yes.
But how it came from the log from the.
It didn't come from here. It didn't come from here.
Okay.
I'm just saying this is all over here. This log 2 would contribute to this, not to the base entropy.
And I'm not following by.
Why? So the human has no entropy in response to this question. Human is.
No, I understand.
Yes. So that's log 1. So okay. So let me. My next slide says this.
I think I can
So-
actually answer the question. It's because if you think about the answer there, the token that says A or D is where this entropy is, but there is a lot of other stuff in the initial sentence and the answer that doesn't fall in the category of the correct answer or not. So that's where all the basic.
So maybe let me clarify. The entropy is just the choice A versus B. That's what you're saying. In that you see, right? The human would say A.
No, I saw that.
It's a 1-bit answer. That's all I'm saying. Yeah. I'll integrate into the theory. Yeah. Any other questions? Okay. So right. So intuitively, as you reduce the excess cross entropy, and you can easily imagine that in real text, there was something else that was following here, where if you had this 50-50 confusion, you would be predicting wrong, right? This is just distilling out that confusion via a question, and that's called a closed question. Okay, so wait, what happened? Yeah, so the point here is, so what is excess cross entropy? So now you might say, okay, if we have to reduce excess cross entropy, let's just reduce that directly. Why are we working with entropy, cross entropy? The answer is excess cross entropy by definition requires a human in the picture. So you would really need to ask humans to rate trillions of tokens to get actual excess cross entropy and then start minimizing it. So that's not how it can happen. Question?
Just in case it's useful and not a diversion, could you define excess cross entropy?
Exactly what it is, So, like you had a certain place in text, you ask humans what the next word is, and you get some probability distribution on the next word. So that's the ground truth distribution. You ask the model, it deviates, and that difference is the excess cross entropy. Okay. All right. So it shows that excess cross entropy, forces the model to reduce its confusion compared to the human. Okay. So now going to our work. So what mathematical understanding is possible for LLMs right now? And as we heard from Ilya's talk, maybe we have 3 or 4 years or 5 years left to figure this out a little bit. So, all right. So what we'll do is, it'll be a statistical framework, so it will not be too unfamiliar. But we will be able to prove generalization to unseen combinations of skills, combinations that were not seen in the data. Scaling law is just assumed as an axiom, and it sidesteps the need for mechanistic analysis of gradient updates. Key assumption, and this is illustrated by the example, the Winograd example, right? There were many skills you needed for that example, even to predict that the answer to the question. So pieces of text involve combinations of random k-tuple of skills. I'll define a random k-tuple and skills in a second, but that's a key assumption. And then the technical driver of the result will be random graph theory, which maybe some fraction of the audience would be reasonably familiar with. And that random graph theory will explain why reduction in excess cross entropy leads to roughly synchronized improvement on individual skills. So it doesn't say completely synchronized, but you can see from the plots that it's kind of synchronized, as well as on tuples of skills. So it highlights the role of skill learning and hints at new ways to learn. Okay. This whole thinking about skills is sort of implicit there. You know, when you saw, for instance, in Sasha's talk, yeah, they threw in some code data and it improves performance on some tasks that are in the evaluation. So it's not clear exactly what even text is anymore. You know, code is mixed in and who knows what else. Synthetic data. So our framework is kind of agnostic about that. Okay, it doesn't use anything about natural language per se, but about these combinations of skills, which could happen with images and all kinds of other modalities. Okay, so without further ado, the setup. So all right, so usual modeling is not conducive to theory because there's nothing there to work with except the cross-entropy laws. So what are tasks? How are they connected to one another? Right? We are trying to make theory about tasks. What are tasks? How are they connected to one another? Where does linguistics and world knowledge and common sense come in, et cetera, et cetera. Although, yeah, Alyosha thinks there are no skills, so I'm put in some doubt about that. But okay.
You didn't tell us what a skill is.
Yes, it's a node in a graph. You'll be happy to know. Okay, so instead of thinking of the corpus as a very long sequence, I'm going to chop it up into bits of a certain size, and I call that the test stream. So we're looking at, this is a picture for test data. Okay, training data doesn't make any appearance because by scaling law we know already what the performance is on the test data. So we're reasoning about test data. So there are pieces of text of a certain size, and a piece of text T has a probability or measure mu2 of T. Mu2 is a measure. Oh, sorry, it should be mu2 over there too. Okay, so that's mu2. And then there are latent skills. And the answer to the burning question, what are skills? It's a node in a graph. So just think of it as conceptually some discrete set, which is, of course, maybe skill is a continuous notion. But it's a discrete set. And they could involve linguistics, logic, world knowledge, common sense. You can open up books on any of these topics and you'll see, types of logical reasoning. You've all seen, like deductive reasoning, modus ponens, etc. So there's a long list you can get. But there are probably many others that we don't know of, because these skills we're talking about, I want to emphasize, these are skills from the transformer's viewpoint. So what I wrote here was, what we humans came up with in trying to formalize it. But really what we're looking at is skills from the transformer's viewpoint, which who knows what it is. Okay, so this is just for illustration. And each skill also has a certain probability, mu1 of s. Okay.
Probability according to what? Like
natural. In this distribution of text. So we'll see. I haven't.
Oh, you mean
let's see. Let me just continue, and then you'll see.
This skill is
relevant for this. Let's see. Yeah, I'm going to. So the mixing assumption is nature picks a k-tuple of skills IID from measure mu1. So from this set of nodes, pick a k-tuple IID, and then uses an unknown process to convert it into a text piece T. So that's going to be a black box in the theory. Unknown process. Has to be. Who knows what that process is? And uses some other unknown process to assign it a probability. That's also black box. Yes?
Isn't the probability of the text implicit based on distribution of skills you're choosing?
Well, but it's an unknown process, yes. It's determined by that, but we don't know that process. So it's very different from usual simple statistical models, where you would say, you take it and then you combine it in a linear way or something. It's not like that.
You're saying the process itself is probabilistic.
Yeah, so the probabilistic is this thing, that it's picking the IID.
But the unknown process is also probabilistic.
Yeah, but that part you can consider it, it's probabilistic, and you pick one sample, yes.
Sounds very much like a topic model.
It does sound like that, except topic model, as I said, is exactly what I said, the linear, and this is not. This is some arbitrary thing. Yes, indeed. Yeah, and how these skills figure in that, we also don't know. Yes?
This includes the process that takes the skills, ignores them, draws a random thing from probability mu2 and generates it.
Correct. Yeah. Yeah. Oh, yes, man.
The graph, you said this graph is sort of like the graph for transformer skills, but then
Okay,
nature
that's the graph.
picks when
That's-
nature.
Yeah. So,
But does nature pick from the same graph or a different?
so nature picks k-tuples of skills, and then this process of unknown processes kick in. So unknown processes are part of nature, but they're unknown to us.
The collection of skills S is the same. Like nature has a collection.
Nature
of
knows
skills,
knows the collection of skills. Yes.
and the transformer has some collection of skills.
Oh, sorry. Nature is assumed to know what transformer skills are. Yeah. Yeah. Yes.
Oh, wait. Apart from what skills are, is there a fixed dictionary of skills that is always the same, or is it possible to?
Yeah, this theory is assuming. Yeah.
Okay.
So the dynamic theory is very interesting, but yeah, this is static. Yeah. Any other questions?
Could you just say, given the k-tuple of skills, nature samples a text from the distribution mu2? Is that what this is saying?
No.
Okay.
Because
All right,
because
so
you know you have
text
to.
and then assign it a
Yeah,
probability.
yeah.
All right, fine.
Yeah.
Is there a sense in which each of the skills can be thought of as something like an attention head and a transformer? Like parsing is that association between different elements?
It's agnostic. Yeah. There's no. I'm not giving it any meaning purposefully, because I think it's fairly general, more than just parsing. You could also apply to multiple modalities, images, whatever. And it could be mixed in. Yes.
Just to help thinking about it, so nature is supposed to model what the orders or the questions or what are you trying to model with nature?
I'm not. I'm agnostic. It need not even be a text corpus. Is that what you mean? There's some things where you're doing a prediction. Cross-entropy is a prediction loss, and we don't know where these pieces came from. This was the process under that. Yes.
Is the process deterministic or randomized?
It can be randomized. This one, yeah.
Isn't in a way the battle half won because we are assuming that nature works on top of these tasks that are coming from this artificial.
We're not assuming anything. I haven't assumed anything. I didn't say what these skills are, whatever. This is how nature.
Nature take k-tuple of skills from those latent skills.
Yes.
So the transformer.
No. I said that you can even think of it that way. It may not. Yeah, it could involve these linguistics, logic. It doesn't matter. Yeah. But I'm just saying that, just cautioning that the set of skills may be much larger. Yeah. Any other questions? Let me move on. I've clarified the scenario enough. Let's let's see if everything gets answered slowly. So here's the thing. So now, how do we test whether the skill is being correctly learned or applied? So the closed sufficiency assumption is that nature knows a set of skills, and it's going to insert a question, multiple choice question, which will test your understanding of that skill. Okay, similar to the Winograd example. And so, in this piece of text, after it generates it, it inserts some questions. Okay. Now those questions are surprising to the model, right? It may not anticipate where nature would put that question. So it's not required to predict the questions in the cross-entropy loss calculation. So the questions just appear and, model doesn't have to predict them. Then it sees the answers in the multiple choice and it can read the answers. And, the assumption is that it's in simple English, so it understands that. and it just has to predict which answer is correct. That's the assumption, okay? And so the close sufficiency assumption is that nature's questions via close prompts are squeezing out the model's deficiencies in understanding. So the deficiency of understanding is the excess cross-entropy, what humans would not have, and the average cross-entropy loss was just, squeezed out as excess cross-entropy on the questions that nature has inserted.
So, sorry, you can think of the prompts as a hint. Somehow, you're saying the hint is very good.
It's not a hint, it's a question, but it's saying that, so if you think of it as hint, you may actually object to this assumption, because you would say, that was a big hint, right? But think about the Winograd example, right? Who was afraid of violence, right? Now, maybe you could say just asking that question makes you think harder, maybe. And then, so you're sort of interfering with the process a little bit.
It's at least not an obvious hint.
It's not it's an assumption. That basically the model's a priori lack of understanding or confusion is squeezed out by these questions. Yes?
And so the closed prompts are assumed to kind of be collections of questions that have definite answers.
Yes, that the human can answer, yeah. You can easily imagine that the human has a certain probability of answering, and then it's an excess cross-entropy. Yeah. Okay. Yes?
So, as it emerged here, interaction.
Yeah.
So having interaction as a way to generate data might be a thing of the future.
Yes.
How would that go into your model?
You would have to extend the theory, yeah. This is a more static theory, yeah.
Can this assumption be empirically tested on a bunch of closed prompt benchmark tests?
That's a good question, but yeah, I haven't.
And it hasn't already been
tested
by others.
Right.
I would argue that it has been in the sense that researchers have
Yeah.
Some
that would be my answer. Yeah.
Like arguably, depending on how you want to define a task, you could say that a given natural language inference is a task, and NLI data sets test that task. So
exactly, yeah. Thank you. Yeah. So Colin is probably one of the experts in designing these evaluations and so on. So yeah, at least I'm glad to hear that he agrees. Okay, so all right, so now measuring proficiency in skills and tuples of skills. So we have this bipartite graph where every skill, k-tuples of skills produce pieces of text. So therefore, each individual skill is involved in some pieces of text. So all right, so so each skill S is involved in a subset of the text pieces. So that's a sub-distribution on text pieces. Right. So if I look at it from the point of view of any individual skills, look at all the pieces it got used in, and that's the sub-distribution. So the observation is that if the close prediction was successful on T, then all k skills were correctly applied. I'm not sure if I should call it observation or that's an assumption. That because we're saying that if close prediction was successful, then you apply the skills. That's the definition. Okay. Now, what happens when the close prediction was incorrect? Okay, so now you failed to predict that it was the councilmen that were afraid of violence. Which of the skills did you fail at? Did you not understand because you didn't understand what are demonstrations, any of those, right? So they're all these skills that were used. We'll assume that they were all incorrectly applied. Yes?
You're saying, what if you apply two skills kind of incorrectly?
So that's what I'm answering. That if the answer is incorrect to the closed question, I'm assuming that all skills were incorrectly applied. So that's a kind of conservative bound, as you'll see.
Sorry, what I'm asking is if you successfully do closed prediction, you could have incorrectly applied two skills that like cancel out, right?
Right. This is ignoring that. It's assuming that at least on average, if you're doing it correctly, then you are applying the skills correctly. Yeah.
Sorry, none of the other n minus k skills are applied. Yeah, isn't that also assumed?
No, well, correctly applied here on this T. That's what I'm saying.
But the T they might have applied other skills as well, more 2k skills on the whole.
No, so that's what we're assuming, that the nature has basically given you a catalog of k skills. Maybe where you're going with is, different pieces of text may have different number k, and that just makes, as you can imagine, the random graph theory hopeless. So I'm keeping it at 1k. Okay, so now the failure rate of the model on scale S is just a loss on close prediction from this distribution. Okay, so that's the answer to your question, Alyosha, that this is, you are basically reducing it to some kind of statistical measure. That's skill. And similar definition with task correspond to k prime tuples of skills, or k prime less than k, like pairs of skills. You take pairs of skills and see which pieces of text they're part of, and then go from there. The model, the analysis doesn't need to know. Yeah. So it's not composition; it's combination. That those two skills appear in that. And if you don't, if the model doesn't solve the close question correctly, then you assume that basically all the skills that were used were incorrectly applied there. Okay. So it's a very conservative estimate. So you're lower bounding how good your proficiency is on the skills. You may be more proficient despite making errors. But if you're making errors, it's assuming you're just not proficient. Okay, so again, same thing. So just to illustrate, suppose nature produced this piece of text using a 5-tuple of skills. Then this piece of text appears in the distribution for 5 statistical tasks for each of those 5 skills. 5 choose 2 statistical tasks corresponding to pairs of skills. 5 choose 3 statistical tasks corresponding to triples of skills, etc. Okay. So there's like a whole universe of tasks. S choose k tasks, statistical tasks. Okay, and then as Colin said, all these tasks that maybe are used in NLP are using some subset of skills. Okay, so why emergence? And so what I forgot to say on the previous slide, that that picture of the scales and so on is called a skill cluster, and you could imagine corpus having multiple skill clusters, and I'll address that later. But for now, we discuss a corpus where there's a single set of skills and then this piece of text. The process I described was one cluster. So how does the model get better? Well, we know, remember, we are assuming that the cross-entropy on the answers to the closed questions is tracking the overall cross-entropy. So as the scaling laws kick in and the model gets better at cross-entropy, you will also see that it's answering the closed questions much better, which are testing the model's understanding. So these are the errors on closed questions, the big X. And as you scale up, the model's cross-entropy improves. And the assumption is that these errors will also go down. So for instance, like this, okay? So something like that. Okay, so as you scale up, the closed questions are getting answered more and more. All right, and so how does this affect error rate on task related to skills and skill tuples? So let me first tell you the incorrect way to think about it, which is that it's just a random graph, so all skills are equally affected. You know, you take any set of places where the errors are happening, and basically every skill will have about the right number of proportion of edges there and so on. That's not exactly true. Okay, so the reason it's not true is that these errors depend on the training process and details of the training set and so on. And so, and then there are these unknown processes that link these different text pieces. So after training, you cannot assume that these edges with respect to where the errors are random. You cannot.
You mean uniformly random?
Uniformly random, yeah. Even if they were put in randomly, conditional on knowing where the errors are, you cannot think of them as a random set of edges.
But you're still using statistical arguments to think
We will,
it.
yeah.
Not a uniform distribution.
Correct. It's just not uniform. Yeah. That's the random graph theory. Okay. Any questions? With all this build up, now I'm ready to give you the theorems. Okay. So, so why emergence? All right. Yeah. Oh, I managed to go back. I see. I got confused. I was holding it. It wasn't making sense. Sorry. Okay, good. Oh, this also is there. Okay, good. Yeah. So what we want is the emergence curve, right? The statistical process that proficiency in tasks increases. It's a continuous thing. And some of the previous talks mentioned that, the illusion that it suddenly emerges is just that, an illusion. And if you do it properly, you should see just continuous improvement as you improve the model or scale of the model. And the curve I'm talking about is, set of x, y pairs, so in a plane, right, in a graph, such that when the excess cross entropy is theta, then for at least X% of skills, the model has classification loss at most gamma on the statistical task associated with that skill. Okay, so I've reduced skills on proficiency on skills to this prediction task, and that's the set of XY pairs. For what fraction of skills the classification loss is less than 1.
Sorry, what is the dependence on K?
So K is going to be in there because, you'll see the expression. It depends on K. Okay, so this is the first theorem. This is for uniform distribution, uniform mu1 and mu2, the two measures. And that's really classical random graph theory. And by the way, this figure was done by GPT-4 in the last minute rush. So that's a conceptual picture, right? These are skills, these are the text pieces, and this graph connecting them is random, even though there are these arbitrary measures and so on. But that measures are now uniform. So the curve that I was talking about is sorry, curve. Sorry, this doesn't seem right. I think there's a typo here. Anyway, the curve that I mentioned is given by this expression. So it depends on theta and k, and then alpha, beta are like the x and y, roughly. But it's in this expression, it's like if excess cross entropy loss is theta, then there are 1 minus alpha times n2 skills, such that model has error less than beta times theta on the task associated. So parameterization involves theta here. Okay. And entropy is the usual entropy. So just to give you an idea, so suppose theta is 0.1, the excess cross entropy is 0.1, and alpha is 0.2, beta is 3. Then for at least 0.8 fraction of skills, the model answers incorrectly in 0.3 fraction. And as I emphasized earlier, this is the minimum guaranteed performance because I have a very conservative estimate of performance. So in practice, the random graph theory may be pessimistic and performance may be better. Okay. So yeah. So and you can see that the random graph theory is coming in because of this for all y. We don't know, what this set is, where the errors are. So we have to reason about all y. So Anyway, so this is for, this is just done by a probabilistic method to show that it holds with high probability for all y. The fraction of y's that violated is 10, or the expected fraction.
Sanjeev, like the thing that's been puzzling me the whole talk is like random graph theory can tell us about like sudden emergence of, you know, connectedness or certain subgraphs or things like that. But here it seems like we only care about k-tuples, right? That like we
So right now I'm only talking about nodes. I'm just talking about skills. I haven't talked about the tuples in this theorem. I'm coming to that. So this is just individual skills, which are nodes.
Right. Okay.
I'm going to talk about tuples.
But then, like, we want to make a statement about like it happened suddenly that like all these skills, you know.
So for that I have to give you the picture.
Okay.
So so this is what it is. You can't wrestle with this anymore. This is what it is, and so we have to plot it to see. Yeah. All right. Oh, and then the weighted version, with arbitrary measures, is just a more complicated version of the probabilistic method, which required some work. So these are the curves, okay? So that's the answer to your question. So, you're not going to get some single expression that describes emergence. It's this collection of curves. And you can reason about the curves based on the math. Am I out of time? Almost, yeah. So this is for k, different k and theta. Theta is 0.1, so it's different k for same theta. And there's a simple corollary of the theorem that increasing k shifts the curve below and to the right. That is, there's better emergence. Yes.
I thought Scott's question was, there's some global phenomenon like connectivity, etc., that emergence should apply to. So what's that global quantity?
Yes. So this is just competence and skills.
Yeah.
So emergence I'm talking about is that your performance on a bunch of tasks improves. And for me, tasks are either, these statistical tasks associated with individual skills or with tuples of skills. And I'm showing the result for those.
Okay, because if there's no global phenomenon, then it seems like we should just be able to write an expression like, whatever to the k power, right? And it should be smooth, right? Like the probability that I have all these skills is equal to, the probability that I have one skill raised to the power of.
I didn't understand that. Probably there's a misunderstanding. Let me just finish. Okay, so the simple corollary is that increasing k shifts the emergence. Shifts the curve below and to the right, and that's better emergence, right? So you have more skills that have good, that similar or better performance. And what is higher k? I think of that as a substitute for data quality, or proxy for data quality. That more complicated data, right? These days, apparently the human raters have to have college degrees, so they can write skills, they can use more skills in a piece of text. So high k is better quality text. Then emergence scores for k prime tuples of skills. This is, I'll just say in one line, it's a tensorization argument for the theorist. Okay, it's a tensorization argument, and that's what gives you that. But the bottom line is that basically, if the size of theta reduces by a factor of 2, then whatever performance you're getting for single skills, you get for pairs of skills. You reduce it by another factor of 2, then whatever performance you're getting for pairs is for the current. So as the models are scaled up, you'll see better improvement on tuples of skills. Yes.
So did you get all pairs?
No. Similar.
Pairs?
It's this curve. Some fraction of tuples, you will see a certain performance. But the overall curve of that is exactly just shifting up.
So does the fraction of pairs of skills that you get correct rise continuously as theta falls?
That is not the claim, because this tensorization argument is not exact. Again, all of these are all underestimating rather than overestimating, and so it's all consistent. But that I don't know how to prove that yet. Yes.
Is it a fair summary of what you're saying? I mean, there's a lot hidden in sort of the formula, but that the emergence of these sort of complex abilities arises as a phase transition due to the non-uniform distribution of degrees of.
It's not non-uniform; it's uniform.
Okay, you were talking about how the distribution over a number of edges connecting.
Yeah. So maybe let me finish and then take more questions if we have time. Yeah, so that's it. Yeah. So, and again, so yeah, you see that, if you increase the scaling by, towards the magnitude, then what was the curve for single scales becomes the curve.
What's alpha again?
Don't worry about it. It's just, the fraction of scales that are, yeah. So, so the point is, you've only had a constant factor increase in amount of data, and you're suddenly seeing good performance on quadruples. So you definitely didn't have a polynomial increase in the amount of data. That's mathematically following. That's the key takeaway here.
Can you repeat that? Sorry?
So, these curves, so what I'm saying is when you increase the amount of data by a factor of 10, the curve for one tuple shifts from here to here, and this becomes the curve for the pairs of scales. You have another order of scaling, 10 factor 10, and quadruple is doing as well as single scales. So your performance on k-tuples or tuples is increasing much more than polynomial, much better than the amount of data you're seeing. It's some kind of a, yeah.
It's another way to think about.
If it's, let's restrict questions to exactly if you don't understand something rather than follow up. So, okay. And so, yeah, this I want to say, but yeah, there's an explanation, like these scaling laws implicitly are suggesting phenomena like these. That, as you scale up, you need less data for the same amount of learning. And that's what's going on. Okay? Much less than a naive counting approach would say. This was an illustrative experiment that, you can learn to recognize 4 tuples of digits, which is 10 to the 4 combinations, from actually 10 to the 3 labeled examples. Or labeled examples in a very different way. So you can read the paper. And extensions of theory, yeah, non-uniform distributions I already mentioned. General skill clusters, you could have different skill clusters like basic English, math, logic, whatever, or science. And you could have different skill clusters. And then, there isn't a clean theory because we don't know if progress happens similarly on all those clusters and at what rate. And so all of that is not, it can only be settled by experiments. Yeah, emergence in different clusters may happen at different scales. Mathematically, that's allowed. And the last thing I want to emphasize, again, returning to this magical ability of chatbots to combine skills on demand. I call, I call it procedural thinking, for want of a better word. I mean, in all of these, we're trying to use 20th century notions to explain 21st century phenomena. And the procedural thinking is roughly that, you're given, describe the task, and then, you're identifying some arguments and some procedure that has to be applied using those arguments. And so that's what we call procedural thinking. And that's somehow emerging. And of course, it's just a tuple of skills. These are all individual skills. You can count them as skills. So they will emerge from scaling, but maybe they can emerge better than that as well. So concluding thoughts, elementary and plausible accounts explains phenomena such as learning k-tuple of skills without seeing it in the training data. Highlights the importance of procedural thinking. And some procedural thinking appears in our theory, just presumably by statistics, but probably there's more going on empirically. And are closed tasks sufficient to test most interesting skills? And cognitive scientists seem to think it's pretty general, if not completely universal. This notion of skill seems limiting. Proficiency on skill is on this distribution. And the whole point of a language model or AI models is that they seem to work outside of the trained distribution. So that seems limiting. So that's just the first criteria. So I'll stop there. Thank you very much.
Let's take one question, and then others can ask Sanjeev at lunch.
So is another way to think about this is that for each of these skills, as you train more, the skills get a little bit better. So it's instead of having a skill or not, just you have different
continuous improvement. Yes, different levels.
And that if it requires 5 skills to do a task, and in each skill gets better by a factor of 2, it's 32 times better to do the task, and then it suddenly emerges that you could do the task.
There's a non-linear like that. I mean, not exactly that math, but yeah.
But that's kind of a qualitative way.
Yeah.
Okay, thank you.
Yeah.
Should we
Sure, you're in question.
Okay, apparently I can do more questions, according to Umesh.
We have the lead doubter here.
Well, okay, so I was trying to kind of reconcile my worldview with yours, and here is one attempt.
Okay.
What if you have a huge amount of skills? If you have skills on the order of the amount of training data,
Then
is
this
that
theory-
going to be okay?
Then this theory doesn't apply.
I see.
Like this is asymptotically assuming.
So you assume that your skills is a very sparse set.
You know, it could be 10,000, 100,000, but it's not tera.
All right. We are still in disagreement.
Okay.
Just a naive clarification. So in this example, based off of that other question of this continuous improvement, like epsilon to the fifth power, at the end of the day, did you have like a nonlinear, were you looking at accuracy or error, some nonlinear metric that you put at the end of that you're measuring?
Oh, I see. So I was assuming
continuous probabilities and.
So yeah, the calculation I was showing was assuming that, you know, if you are in that set of theta where, you know, by averaging there's like error at least half or something on the closed question, then you've completely failed. That was the assumption. I was not taking that thing in account. Yeah, it's just assuming it's completely failed. Yeah.
So, Sanjeev, just wondering if you feel comfortable with the elbow level that we are achieving. The initial empirical graphs you showed almost at a phase transition, almost zero.
Yeah, but it's on a log scale.
Yeah, it is on. Okay.
So remember that that we think that performance goes with excess cross entropy, right? Not cross entropy. They are doing cross entropy, right? So when excess goes down by a factor of 2, it may almost not show on the graph, but it's massive for classification.
So I do NLP, so I don't really understand math, but my question would be, so like what is the most surprising empirical phenomena that you think your theory can predict that we could not predict if we haven't listened to the talk?
I'm asking you to focus on this magic that, you know, you can give GPT-4 at least, and maybe the other models too. Like a large, take any set of skills, reasonable set, and take 5 tuples, and it can compose them. Now that's not AGI, but I'm just pointing out that that's not enough data in the training set to do that. Maybe that's one key takeaway. I mean, even if the theory doesn't impress you, like that's fine, but that is very counterintuitive. Yes.
Rephrasing.
Yes.
You started rephrasing. You started with the sentence. You're saying, okay, a few years ago, get it wrong. Now you can get it right. So there was some
get it wrong. Meaning?
The they.
Oh.
You know, the policemen, the demonstrators, whatever.
The language models got it. Yeah.
And your theory was saying, okay, all of a sudden with this emergence of skills, graph theory can maybe explain to us why these would emerge. But another way to ask it about being actionable, can you say how much data you need? Can you pull out how much data you need out of your formula, out of your analysis to say when some other set of skills would emerge?
Right. So the problem here is that, you know, what Alyosha is not happy with. What is a set of skills? So this is a qualitative theory in that sense, right? Like, do you have a complete cataloging of skills? Nobody.
You can't have it both ways.
Yeah.
I mean,
So right, so it's a qualitative theory completely. I completely agree. Yeah.
So, Sanjeev, like I obviously had at most K-1 of the skills needed to understand this talk. maybe I can rephrase my question this way. Like, why is it not obvious? Like, as I improve each of my individual skills, I will also improve on, you know, any subset of K of the skills at some rate that I can calculate. Like, why do I need graph theory to tell me that?
So the driver is not that you're improving the skills. Driver is you're reducing cross entropy.
Okay.
So it's not even trivial to argue that if you, so like you have now 1% of the training set where there is errors. What is the fraction of edges from individual nodes on the other side that are going to that set? It's an arbitrary set.
Okay, I think we should break for lunch.
Okay.
Yeah.
All right. Okay.
So we'll come back here at 2 p.m.